Okay, today we're going to be looking at the movement of a charge in an electric field, potential difference, and electrical energy. Now, previously we were considering particles in an electric field. So, say this is our electric field, and we considered a particle in the electric field, and we were considering this particle as being fixed. Now, what if a particle is moving in an electric field? So this leads us to the concept of electric potential energy. And as before, when we were considering our electric field, and we were looking at how there's the parallel between our electric field and a gravitational field, we can use the same analogy, we can use the same concept. So let's consider a gravitational potential. So we've got a crane, and there's some mass, and this mass is going to be lifted up some distance. So we hook there, D, and there's a force lifting up, F. And we know that we know to lift a mass some distance against gravity, work must be done. Work is done to lift something to height D. Now, once the mass is at point D, that work done takes the form as gravitational potential energy. So the work done is converted into gravitational potential energy. So the work done, so let's call this EW, is FD, and that then gets transformed into gravitational potential energy. The same principle is at work within our electric field. If we have a unit of positive charge and we want to move it to another point in our electric field, work must be done. The work done is the electrical potential energy gained by a single positive charge. So let's draw a wee diagram for this. So we've got a plate here and a plate here. And this is a positive and this is our negative, and we've got some charge, some positive charge, and we want it to go in this. This is our electric field, and this positive charge is going in this direction. So there must be a force acting on it. Work must be done against the electric field for this particle to move. This means the electrical potential energy is a measure of how many joules of work have been done to move the single coulomb of charge to its current position. So just like with our mass being lifted up, if we take this charge and we move it from here to here, we're doing work done against the electric field, and then when it's at this position, the charge is going to have electrical potential energy. This work done will be converted into electrical potential energy. So the electrical potential is equivalent to, this is the sign for equivalent to, the work done over Q, which EW is electrical potential work, energy, electrical potential energy, or work done, and Q is the charge. Why have I done two C's? Tidy that up. Is the charge, and that's in coulombs. Sorry, I wrote the coulombs, and obviously the work done is in joules. This electrical potential is often just called the potential, so we can call this also the potential. And it's measured in volts. So 1 volt is the equivalent of 1 joule of energy being used to move 1 coulomb per coulomb. So 1 volt is 1 joule per coulomb. Now let us think about this a bit more deeply. So let's go back to our analogy with gravity. So we've got a table here, and we've got an apple, and we move the apple onto our table. So what we've now done is we've done work done, put it on the table, and this apple's now got gravitational potential energy. But let us consider something. This table is on the second floor of a building. So second floor. So when we were in the room here, we considered the gravitational potential energy of this raising onto the table, but this apple's actually got the gravitational potential energy of this whole height here. And the same principle is at play with electrical, of an electric field. So let's consider two plates again. This one's negative and this one's positive, and we've got charge plus Q, and we're going to move it to here. Now on the right here, the particle starts with 5 joules of energy, of kinetic energy, but then we use work to move it to this position to the left, so it gains QV, work done, energy to move it to here. But therefore the energy here is not just the work done that we gave it to move it. It already had 5 joules of energy, so the total energy is going to be QV plus 5 joules. So instead of talking about just the potential, we consider the potential difference. So when we refer to voltage, we're actually meaning potential difference. And it's measured in volts, obviously. So the potential difference, V, is this EW over Q. In most cases, the starting point, for the voltage potential difference is the starting point will be defined as 0, and then we'll have some other positive potential. Now, when we have a battery, a negative terminal, the negative terminal will be 0 volts, and the positive terminal will be 1.5 volts. In many cases, we're interested in calculating the work done in a field. So in other words, this would be the work done in the field would be the charge times the potential difference of voltage. So this is the work done. And more commonly, you'll see it written as work done, W, is equal to Q, V. Let's now consider the movement of charges. So charged particles experience a force in an electric field. And this leads to acceleration. Now we're not going to calculate the acceleration of charged particles in the fields in this course. But we can work out the velocity of a charged particle at any given position within that electric field. So if we know the work done, we can calculate the velocity using the energy conservation principle. So let's consider this situation. So we have two parallel plates. This one's at 0 volts and this is at 5,000 volts positive, and we have an electron here. We want to investigate what the velocity of the electron would be if it's ejected from this 0 volt plate, and we can view this as being the negative plate, and then what the velocity will be as it moves to the positive plate, the 5,000 volt plate. So we know that the charge of an electron is equal to 1.6 times 10 to the minus 19 coulombs. So the work done moving the electron from here to here must be Q times V, where Q is our charge and V is our 5,000 volts. And if we do that, we get 8.0 times 10 to the minus 16 joules of work is being done. Now, energy must be conserved, And we assume no energy, let's assume that no energy has been lost during the movement of the electron. So this means that the work done must be equal to the kinetic energy, which is equal to half mv squared. Now the mass of an electron is very small, but we can measure it, is 9.11 times 10 to the minus 31 kilograms. And so we can work out the velocity. So we have 8.0 times 10 to the minus 16 joules times 0.5 times the mass, which is 9.11 times 10 to the minus 31 times v squared. Crunching all the numbers, we will get v is equal to 4.2 times 10 to the 7 meters per second. Now, you need to note that in this calculation we have assumed two important things. First, we've assumed that gravity is not having any effect on this system, and secondly, we are assuming that there is no relativistic effects involved in this, and when you're moving electrons, there usually is like relativistic effects. But for this example, we are assuming that these are not the case. We can use the same principle to any particle, as long as we know its charge and its mass. It's also to be noted that in a uniform wait a minute, what am I writing? In a uniform electric field, the potential is evenly distributed. So say you've got a parallel plate and the at 0 to 100, the midpoint here would be 50 volts. The midpoint here would be 2500 volts. Let's look at another example. So we've got this setup here. So we've got parallel plates, and this is at 0 volts, and this is at positive 12 volts. And we have the potential difference at different parts are, this is 9 volts. In the middle, this is meant to be the middle, by the way. It's obviously 6 volts, because it's half of 12, and down here 3 volts. So we want to calculate the velocity of 2 times 10 to the minus 19 coulombs of positive charge at point P. And point P is going to be here. It leaves the 12 volt plate at rest, and the mass of the charge is equal to 5.0 times 10 to the minus 25 kilograms. Now, we know that the mass, we know that the particle that's moving from from towards the 0 volts plate is positive, and we know this shows the midpoint and has a potential difference of 6 volts. This means the potential difference between 12 and 6 is obviously 6. So we can work out the work done. Times the 6, and that's going to give us 12 times 10 to the minus 19 volts. Next stage, we use energy conservation principles. So the work done must equal the kinetic energy, which is equal to half mv squared. So 12 times 10 to the minus 19 must equal half times the mass was 5.0 times 10 to the minus 25 v squared. Then so the v will work out at 2,191 meters per second. So I hope that helps.